Now I'd like to introduce you to the 8x8 dual color LED matrix. We'll look at its wiring diagram, electrical interface, and a raster display technique. This is the 8x8 LED matrix that's included in the NI myRIO Embedded Systems Kit. Each dot on the array contains one green and one red LED. If you activate both of them at the same time, you can get yellow. Here's the wiring diagram. First of all, to get you oriented, when you're looking at it from the top, you'll see these four tabs. These tabs on the top and left side of the array are intended to fit into the insets on the right and bottom side of the array. This way you can make a seamless panel as large as you like. Now let's take a look at the pin connections. Looking down through the array, you see a total of 24 pins. This is pin 1 on the lower left corner. You have an ascending sequence up to pin 12. This is pin 13 in the upper right, and then pin 24 is located right here. Now each dot in the array contains one red and one green LED. The cathodes, that is the side of the LED with the bar symbol, the cathodes are all wired together along the row. This is row 1 on top. The anode of the green LED in each dot is wired to this common vertical wire called C1G for the green, and a similar vertical wire for the anodes of the red LEDs. Now each of the 8 row wires is connected to the pins like this. We have pins 1 through 4, then pins 21 through 24 located like this. So all of the row wires are on the far left in terms of the pin arrangement. All of the green columns are wired like this in order, 5 to 12. The red columns are wired also in order, 20 down to 13. So the wiring is actually very systematic and easy to follow. Well, let's see if we can develop a better understanding of the electrical interface. Here's a single dot. We have the green LED and the red LED. I'm going to define the diode current as ID and the diode voltage as V sub D. The green LED requires about 3.5 milliamps at 2.8 volts, while the red LED requires a little more than 10 milliamps at 2 volts. We see that the red LED requires much higher current at a given voltage. Now, to activate the LED, you might use a circuit like this, connecting a battery and a current limiting resistor all in series with a diode. The current limiting resistor adjusts the diode current, which in turn controls the brightness. When the diode is on, the anode is at the high level voltage and the cathode is at the low level voltage. Now on the NI myRIO, I'm going to replace both connections along the row and the column with a digital I/O. The myRIO DIO in output mode looks like a connection to ground via approximately 65 ohm current limiting resistor. And in a similar fashion, the high state DIO looks like a connection up to 3.3 volts. Now, using these specific values for current and voltage, we see that 3.5 milliamps going through 65 ohms gives us a drop of 0.23 volts. That means that the DIO line from the myRIO is actually pushed up to 0.23 volts from ground. In a similar fashion, this line is pulled down a bit to approximately 3.1 volts. Now let's consider turning on the red LED at the same time. As I mentioned earlier, this has a higher demand for current. As this current works its way down to the common row line, it's going to push up the DIO pin voltage even higher to at least 6.5 volts and above. That means that the green LED voltage will go down, and at the same time its current will also go down. That means that the green LED becomes much dimmer. So in effect, the red LED, when it's active, steals current from the green LED, and that suggests that you do not want to activate the green and red simultaneously. But that leaves the question, how do you get yellow? And so that question leads us to the raster display method also known as a multiplexed display. This facilitates arbitrary LED patterns and also balances the LED intensities for a better yellow mix. I'll show you how this works. Here's the rows. Let's initially set all of the row lines to a high level. That effectively disables all of the rows. Here's all of the red columns. I'll start with those all low, and that effectively disables all of the red LEDs. Similarly, we'll set the green columns to low as well. Now I'll begin by causing row 1 to go to a low level. Now all of the LEDs remain dark because all of the column lines are still low, but let's cause one of them to go to the high level. Now the entire column line is high, but there's only one place where we have a intersecting row line that's low. That means we would light up a single LED. Again, as long as all of the other rows are disabled, we only activate a single LED. However, within a given row, you can turn on more than one LED simply by causing additional column lines to go to a high level. Now, while I still have the first row enabled, I'm going to enable the column line for the green LED. In a similar fashion, there's only one place where we have a combination of high and low, and we light up just one LED. Next, you would disable row 1 and then enable row 2. Apply your patterns for both red and green, and then that would take care of illuminating this second row. You would then disable row 2 and move on to row 3, etc., and so on. And that means you would walk that low value to each row and then repeat. The overall sequence looks like this. Set all of the rows high. You enable row 1, apply the pattern to the green columns, and then disable all of the green columns. Apply your desired pattern to the red columns, and then disable the red columns. And then go back and repeat for row number 2. Finish out the rest of the sequence, come back around, enable row 3, and so on. So essentially you enable the next row until row 8, and then you would repeat with row 1. Now you have to continually repeat this sequence so that each LED is refreshed at least 30 times per second. This is called the flicker fusion rate, and it's a property of the human vision system. That means you need to do this sequence about once every millisecond. I'd like to point out that it's important to bracket the sequence with all LEDs disabled. Specifically, do not change the rows while you have an active column pattern applied. For example, if we were switching from row 2 to row 3, when you look at the details, you have a little bit of overlap as row 3 goes down while row 2 goes up. Now, if you have an active column line during this overlap period, you will see that the next LED starts to turn on. It's very faint, but you see an undesirable ghosting effect. All right, I'd like to close out by looking at a specific raster display example with the real hardware. And I think this will help you to more firmly grasp this notion of the raster display style. Right now I have a 1 second update interval. You'll see that I'm alternating the red and greens and working from top to bottom as far as the rows are concerned. All right, let's speed it up. This is 3 times faster. All right, I'm going to gradually increase the speed going from top to bottom. And somewhere around 3 to 2 to 1 milliseconds, the display fuses together into something that appears to the eye as stationary and completely flicker-free. It seems to flash here. That's an artifact of trying to capture it with a webcam.